After watching this video lecture, students will be able to understand the origins of the orbital models with respect to quantum mechanics. They'll be able to explain probability distributions of electrons. They're going to be able to identify shapes and directionality of the s, p, and d orbitals, and be able to identify the number of electrons that can be held in each orbital subshell. So a new approach to atomic orbitals and atomic structure was brought about by Heisenberg, de Broglie, and Schrödinger. And basically, de Broglie compared matter to a standing wave in something like a stringed instrument. So basically, you have nodal planes, so basically locations where there is no wave. And then you have areas where there are waves. And in these areas, you specifically have a whole number of waves present. So the understanding of the waved instrument is not important. But what's important is that the comparison that was made allowed Schrödinger to come up with a mathematical construct that gives us the structure of atomic orbitals as we understand them today. So as I was saying, when it comes to the waves associated with the stringed instruments, you have these whole numbers, and there's only specific waves allowed depending on the string that's being plucked. In that same way, electrons are only allowed to have certain waves. And basically, what Schrödinger did is he described the wave with respect to a mathematical function. And there's a lot of calculus involved in the calculation, but we don't really need to know that for this class. That's a PChem type of approach, and you guys will have that if you decide to continue with chemistry into college. So Schrödinger's equation were represented by values here. This is a Hamiltonian operator, the symbol psi. The energy associated with this wave function and the details of the wave function need to be understood with respect to the wave function is with respect to an x, y, and z axis. It's a three-dimensional type setup, so that's what's going to give us our orbitals. The Hamiltonian is an operator, basically tells you what kind of mathematical functions to carry out on the function, and E is the energy of your atom, or the specific atom that you're looking at. So the solutions to Schrödinger's equation give you orbitals, or orbitals as we understand them today. And basically, the solutions that we get to these equations are not Bohr orbits. So we know from the model, from what we've seen in other chemistry classes, we understand that the electrons in an atom do not have these circular orbits. Okay, so the Bohr model doesn't really actually happen. It's much more complicated than that. And the last thing we understand about Schrödinger's equation is basically that the energy levels, or the solutions to Schrödinger's equation are going to be tied to specific energy levels. So the solutions are going to tell us information about the orbitals, including things like shape and things of that sort in the 3-dimension. And it's also going to detail the energy associated with that specific orbital set. So the wave function doesn't really tell us anything by itself. It's not really possible to map it visually. However, if you take the square of the function, that indicates the probability of finding an electron near a particular spot. And this is called probability distribution. And basically, when we map these, it allows us to see the most likely location of where the electron will be found within the atom. So basically, it's a probability distribution for specific electrons. As we know from other classes, probability distribution is what tells us where the electrons reside. Where the electrons reside are known as orbitals. So this wave function actually tells us, quite a bit about where the electrons are, what their relative energies are, things of that sort. So radial probability functions basically tell us the probability of finding an electron at a specific distance from the nucleus. And so if we look at our functions, our radial probability functions here, you notice that there are humps, basically. These large humps indicate the most probable distance that electron will reside in from the nucleus location. So basically, the bigger the hump, the more likely the electron is going to be there, and its distance from the nucleus is indicated by the radial distribution along the x-axis. So the 1s has this hump here. Your 1s electron is going to be as close to the nucleus as possible. If we look at a 2s orbital, we have one hump here. Notice the most likely distance is, approximately 3 angstroms from the nucleus. However, there is the small possibility that it'll be closer. If we look at 3s orbitals, okay, there are a few other locations, but the most probable distance is approximately 7 angstroms. Now, I also want you guys to notice basically the points where there is 0 probability of finding an electron. And these locations on these radial probability functions are called nodes, and that's the location where you have 0 probability of finding an electron. And so basically, when you utilize Schrödinger's equation, you get locations where you will have electrons from the calculation, and you get locations where there are going to absolutely be no electrons. And so basically you have two components, where electrons can be and where electrons are not going to be. And this does connect somewhat to the wave representation in a stringed instrument. If you go back to the original slide, you'll notice that there were locations where the wave had amplitude, it had height, and then there were basically locations, or those nodal locations, where there wasn't any amplitude. So there is connections. If you want to read more about the connection between the two, you can. Just the main understanding is that these calculations are taking these wave properties, properties of electrons, and allowing us to figure out their location with respect to the equation. So the size of orbitals are basically where 90% of the total electron probability resides. So what does that mean? That means that an orbital is going to be dictated by where you have a 90% chance of finding the electron. Okay, so unlike Bohr's approach, they're not going to be a certain distance. The electron is not going to reside at a certain distance, but a most probable distance. Remember, we're looking at a probability curve. We looked at radial distribution curves. Remember that there, in the 2s and the 3s example, there were locations where the electron could reside that were closer to the nucleus. You saw multiple humps on both of those examples. However, most of the time, the electron is going to reside with the largest hump, as we saw on the curves. And so, we typically look at our orbitals with respect to the most probable location. However, understand there are potentially other distances that could be being utilized because of what we saw on those radial distribution curves. So the first solution from Schrödinger's equation was for the 1s orbital, and it's spherical. It looks like this, and there's a 90% probability of finding an electron along this sphere. However, there are many other shapes available, and then basically these shapes are derived from the nodes and the density probabilities. S, P, D, and F orbitals are what we're going to need to know for this class, and you guys should be able to identify their shape and their various orientations. So the s orbital, as we indicated, it's spherical in shape. Basically, if each s orbital is able to hold 2 electrons. We'll talk about those details a little bit later. The energy and the orbital size increase as your principal number, quantum number increases. So if we're dealing with a 1s orbital, it'll be spherical, but the electrons that are there will be closer to the nucleus than, say, a 2s, an electron in a 2s orbital, and that trend continues with a 3s orbital. So both energy and size increases as we go from a 1s to a 3s orbital. p orbitals have this dumbbell shape. It does have a node. Okay, remember a node is a location where there's a 0 probability of finding electrons. So notice the nodes are here, in between here, and in between here. So these basically bubbles are the high probability areas of having electrons reside, while the nodal points between the two areas is where electrons will never be. Now, when you have or you're dealing with p orbitals, you're dealing with a set of 3. So each p orbital can fit 2 electrons, but when you have your 3 p orbitals, you can fit a total of 6 electrons. Now, what's different between the s orbital and the p orbital is that each p orbital has directionality. It has an orientation along the x, y, and z axis. And we differentiate these orbitals to identify types of bonding and things of that sort. Remember that these are solutions to Schrödinger's equation, so these are not just made up, they're actually connected to a mathematical construct. Okay, so what I want you guys to notice is how we name these. Okay, so we're talking about, in this specific case, we're talking about 2 p orbitals. So that 2 is identifying your principal quantum number associated with the electrons and stuff that are being looked at and put into these orbitals. Now I want you to notice that you have the 2p sub x, 2p sub y, and 2p sub z. So we would call these the 2px, 2py, and 2pz orbitals. And what I want you to notice is that the subscript x, y, and z is an identifier in terms of the orientation along the x, y, and z axis. So 2px, notice that the p orbital lies along the x-axis. Okay, the 2py, it lies along the y-axis, and the z, 2pz, lies along the x-axis. So basically, the directionality is dictated by these subscripts, and they're actually a specific orientation in space. You would want to identify that so that you could be comfortable with organizing these in a way that matters. So if we were to have all of these, be looking at a specific example with all of these types of orbitals, we're not going to have 3 separate axes. Remember that these 2p orbitals are all on a single atom. Okay, so if we were to look at these with respect to basically being on a central atom, they would look more like this. So you would have your 2py. You'd have them running here along this y-axis. Okay, and then you would have also your 2pz along the z-axis. So they would be clustered all together. And this type of stuff is going to be important when we talk about bonding in a couple of chapters from now. Double bonding, triple bonding. The orientation of these types of orbitals is really going to matter. So we'll talk about that more specifically later. But for now, you need to understand and be able to identify the orientation of the x, y, and z p orbitals. You need to understand that each one of them fits 2 electrons, but when they're all together, that gives you that total of 6 electrons that you guys have been used to. And obviously, their shape, which is dumbbell. D orbitals are basically generally clover shape, although we kind of have one over here that has a kind of a dumbbell slash donut shape going on. Basically, d orbitals, there's 5 of them. They fit a total of 2 electrons each for a total of 10 electrons for all 5 d orbitals. These also are obviously oriented along an x, y, and z axis. However, what I need you guys to notice is that they can be on axes, like we see with examples here, but they can also occur between axes. Okay, so the orientations are somewhat different than what we see with the p orbitals. The p orbitals are actually on the axes. With d orbitals, there's different orientation options. So let's go ahead and look at how we detail these clover-shaped orbitals. So if we look at this first example here, we have a dx sub xz, or dxz orbital. The reason why we call it that is because it is lying, or the orbital itself lies between the z and x axis, so it's the dxz orbital. If we go over here to this second option, notice that we have the dxy orbital, and we have that because the clover-shaped orbital is lying between the z and y axis. Okay, so notice it's lying between this plane, while this example here is lying along this plane. Okay, so these would basically be 90 degrees from one another if they were all on a central atom. Okay, this example here is the dyx orbital. Okay, once again, because it's lying in between y and x, so in this case, this orbital would be 90 degrees and basically laying along this plane that you see here. And then we have the dx squared minus y squared. This example here, this orbital is actually lying on the plane, okay, and along the axes. So y and the x axes pass directly through that orbital. And then last but not least, we have the dz squared orbital. As you see here, it's kind of this donut shape. You have a probability of having electrons around the axis. So the dz square orbital basically has a possibility of having electrons all around the x and y axes, as well as along the dz. So the d orbitals, obviously they're clover-shaped. Some of them lie along the axes. Some of them have electron density probability between axes, as we see primarily with these. But understanding their orientation, their shape, their identity, those are the expectations. Remember, there are 5 d orbitals. Each one of them holds 2 for a total of 10 electrons possible in the d orbital set. And our last set of orbitals that we're going to be looking for in this class are f orbitals. I'm not going to expect you guys to identify these. We kind of go from, okay, we can follow what the d and the p and the s orbitals look like around the axis, to basically getting these really crazy unique shapes. Although we could identify them and deal with them, we don't deal with f orbitals with respect to bonding in this class, so it really doesn't matter. But I do need you to understand that there are 7 f orbitals. Okay, each one of them fits 2 electrons for a total of 14 electrons in the f orbital set. And just like the others, they do have different orientations around the x, y, and z plane. Those axes allow us to differentiate between the different types of f orbitals. However, I'm not going to require you to know how to differentiate between the different types of f orbitals, but I do expect you guys to be comfortable identifying, drawing sp and d orbitals. So make sure you spend time with those, understand, these features of the f orbitals, and you guys will be great with this.